We're now going to be talking about LLMs and software verification for the next two talks. So the first talk is going to be Igor, Engel, and a large team, mostly from Jetbrains, I think. Are you all from Jetbrains? All from Jetbrains, talking about whether LLMs are ready for software verification.
Hello. Hello. My name is Igor Engel, and I'm here representing Jetbrains research. Also, we have Anton Podkopaev on the conference. Yeah. So, my talk is about whether LLMs are currently ready for software verification. What is software verification and why do we want it? So, here, for example, we have a program in Rust that computes a sum and the product of numbers in a vector. And it currently has an anomalous error, which normal tests would likely miss. When we compute the product, we can likely overflow if we have large enough numbers. And normal methods such as linters and tests will likely not catch this. But if we augment our program with preconditions and postconditions, we can run a verifier on it that will tell us that actually those conditions are not fulfilled. Our result won't equal the product of the numbers. And this is the main idea of software verification, which we take a normal, mostly normal language, augment it with preconditions and postconditions, and use an SMT solver to verify that those postconditions do hold. And in general, we also need to provide invariants for loops, because this is something that can be derived automatically. We have in our work explored three verified languages, which is Daphne, which is ground-up built language that includes software verification. And also we have Nagini and Verus, which are Python and Rust respectively, augmented with verification on top of them. So here's an example of our program with verification. We have a precondition that our vector is not too long. And we have our postcondition that we have our result match the sum. And if we can compute the product, we have the result match the product. And then we have some additional instructions in invariants and proofs that help our solver to verify that those postconditions do hold. And this part we call the specification, and this is the proof. And the rest is implementation in normal base language. And so in automated software verification, we want to generate some parts of this. And depending on exactly which parts we generate, we call it different modes. So, for example, in mode 1, we generate only the proof. We are given the program that is already implemented and has a specification, and we want to prove that this specification holds for the implementation. In third mode, we generate proof and the implementation. So we have basically a task description in the form of specification for the program, and we want to generate a program that conforms to this specification. In fifth mode, we generate both. We have only text description of the program in natural language, and we want to generate a specification, generate code for it, and prove that the specification holds. We also have some other modes like 2, 4, and 6, but they're less relevant to this talk. You can see them in our extended paper. So here's an example of ground truth program, which has everything: specification, implementation, and proofs. To go to first mode, we remove this proof, ending up with something like this. We have specification and implementation, but no proof. And in this way, the solver currently can't verify that the specification holds. To go to third mode, we also remove the implementation itself, leaving us only with function declaration and specification for it. And in fifth mode, we remove specification in SMT language, but we add text description that describes what should our program do. So here's our general pipeline, which is we preprocess some code like removing elements from ground truth. Then we go to LLM and ask it to fill in the blanks. Then we check using our SMT solver, our verifier, that we have everything correct. If we have an error, we go back to LLM and ask it to fix it. And if everything is correct, we say that we pass. So what kinds of error can we have? First one is we can have a verifier error, which says that we do not have enough proof to say that our specification is satisfied. So here's, for example, we have an erroneous code in the loop, and our verifier will say to us that we don't have postcondition satisfied. But we can also have more subtle error, for example, in fifth mode, where we also generate specification, where we can have too weak specification for a problem. And in this case, verifier will not give us an error. So how do we deal with this? We introduce what we call validation, which is we ask whether the specification for our generated code implies the specification for our ground truth. So we allow LLM to make our specification strictly stronger, but we want our verifier to be able to prove that original specification holds. And this allows us to deal with errors that arise in generating specification. So a more detailed pipeline is that we have both verification, that is our base SMT language, that checks whether the implementation holds to the specification. And then we have validation that checks whether our specification is correct for this program. Our prompt structure goes something like this. We have a description of a mode in which we are currently running our evaluation. We possibly have some language hints because while LLMs work good with Daphne, Nagini and Verus are sufficiently obscure languages that LLMs often make basic mistakes in them, and that helps to provide some hints about these mistakes. We possibly also have code samples that do work for the same reason. It's good for LLM to have examples to work from. Then we have textual description of the program for modes in which it is used. And then we have our input code, which is prepared from ground truth with proofs and so on strict. When we get an error, we ask LLM to fix it, and provided with an error, provide to us by verifier. And to actually evaluate everything, we need benchmarks. And that's sort of the main problem, because verified languages don't have good benchmarks. Our main solution to this was to take human eval benchmark from OpenAI, which is written in Python, and translate it to our free verified languages manually, introducing specifications for each problem. We also looked at Daphne Bench, which was released quite recently, which is a collection of programs on Daphne, scrapped from the whole internet. And we also evaluated on it, but you can look into extended paper for detailed results on that. So for our benchmarks, we produced in the end 3 separate benchmarks: human eval Daphne, human eval Verus, and human eval Nagini. They are sort of different amount of programs because not everything can be trivially translated into verified languages. Some of it is used non-verifiable features from Python. And here's our main result, which is running Claude 3.5 Sonnet on our benchmarks. And here you can see we achieve up to 86 performance on Daphne. The rest of the languages are less performant because they are less represented in LLM training data. And mode 5 is similarly slightly less performant because it's a much harder problem. We have to provide correct specification, not just follow it. But for modes 1 and 3, we achieve very good results, at least on Daphne. If we break it down further, so here's an example of a Daphne, we see that in some cases we completely fail to provide a coherent verifiable program. But in most cases, we actually provide a program that verifies, but it fails to, so this is mode 5 specification, it fails to conform to specifications which we have given. In some cases, we do, after a few more steps, conform to the specifications, and in quite a lot of cases, we do successfully conform to specifications on the first try. This highlights that our validation is indeed an important step, that highlights some problems that can be found in generated code, because it's not guaranteed the specification will be correct. So next potential steps is introducing more fine-grained validation. So for example, using tests from human eval, not just require exact match with our specification that we have given. We possibly consider fine-tuning LLMs on underrepresented languages such as Nagini and Verus to improve performance on them. And we are also looking into synthetic datasets to provide a more comprehensive benchmark. So in the end, we have 3 benchmarks for verified languages that can be used for further evaluations of LLM. We evaluated current LLMs such as Claude and ChatGPT on those benchmarks. And we have a decent success rate for generation of verified code. Thank you.
Are there any questions? Now, I promised I would throw this instead of passing it around, but perhaps that's best not.
Yeah, no. Thank you very much, and thank you for the very interesting presentation. So my question is regarding, I would like some information regarding the size of the snippets themselves, and if you noticed any correlation between scaling up the snippet size between the actual success of verification or validation through the process.
So we have observed the relation between specification size and success rate, not so much implementation size.
Okay, thank you.
Well, thank you. I got a similar question. So could you say something about the kind of data structures in the programs and what that how that influenced the success rate? Like, is there pointer structures or just arrays or numbers?
So yeah, human eval mostly relies on arrays. In Daphne bench, we have more complex data structures, but we haven't conducted a particular experiment to see how they impact things. But we expect it to be mostly fine with handling data structures.
Should I?
Thanks. So I had a question. So your diagram has pre-processing at the beginning, and I'm sure you told me this, but what exactly does pre-processing involve?
So most of it is preparing our code for a given mode, so stripping unnecessary elements that we don't want LLM to see, introducing our validation technique, and for some languages we want to a bit simplify them because LLMs are not good with some of the features of Verus, for example.
Okay, and I have another question. So the human eval benchmark set, I think, exists for Python, right? And Nagini is verifying Python. So how do your results compare? So from what I understand, when you do a standard like evaluation on the human eval benchmark, you give it this natural language description and some input-output tests.
Yes.
How do your results compare to that?
So we have slightly worse success rate on our generation than with human eval, but we are also solving a harder problem.
So is that worse success rate because when I run my standard human eval evaluation, it's generating some code that will fail your verification?
Some of it, yes. So for example, there is a benchmark called human eval plus, which is human eval with additional tests. And they do find that some of the solutions produced on human eval are actually incorrect, but they do pass the test present on human eval. Some of it is just, we require a stronger claim than just having a correct solution. It has to be provably correct, which is also harder than just having it correct.
Okay, I was just wondering if you could combine the two approaches, if you could generate with the standard prompts in human eval and then have a second step where you add your specs.
Well, basically, this is sort of what mode 1 is like. We just generate the proof for a given implementation.
Okay, thank you. Are there any other questions? Ideally close, so I can test my throwing. If there are no other questions and the next speaker is ready, then I suggest we move on to the next one. Yeah, good. Okay, let's thank the speaker.
So sorry.
No, it's good. Please introduce yourself.
Hi, my name is Daniil. I'm from KIT in Karlsruhe, and for the past year or so, we've been working on trying to leverage LLMs for deductive program verification. This is joint work with Bernhard Beckert, who's also here today. And I mean, you've also already heard a little bit about program verification just now, and we kind of asked a similar question, namely, we've seen that large language models are quite good at generating code. So kind of the natural question to ask is, can they also specify code? And since I'm working in a group that has been developing a tool for Java verification for quite some time, we thought, okay, let's look at this for the case of Java. There's this thing called the Java modeling language, which allows you to specify contracts for Java programs. So for example, in this case, we have a maximum method, which gets an array of integers, and it's supposed to give out the maximum. To that end, we've already come up with a contract that specifies these behaviors. In particular, we want that the output is larger than all the elements in the array. And furthermore, we want that the output is an element of the array. But now, if we wanted to prove this, what we would need to perform this proof is an deductive invariant for this loop inside the method. So essentially what this loop is doing, it's going through the array and looking whether the current element is larger than the current maximum, and if so, then it sets a new maximum, and so on and so forth. And I wasn't sure what kind of background to assume here, since some people might also come from a mathematical background. But essentially, you can think of this as an inductive argument, an inductive proof on why this program is correct. Essentially, this loop invariant, first of all, describes that after the first loop iteration, before the first loop iteration, the formula holds, that it is preserved by a loop invariant, by one iteration of the loop. And then finally, if we want to prove this contract at the top of the method, we also must ensure that this invariant is strong enough that it implies the postcondition. Additionally, things that are often used are loop variants, which kind of tell you that the loop eventually terminates by kind of giving an integer which is decreasing but always staying larger than 0, and an assignable clause, which is kind of describing which variables on the heap might be modified. Right, and so the idea would be, well, it's tedious to write this by hand. As you can see, it's quite long what we have to write here, right? We have to say that so far we found the maximum, that so far the value in max is inside the array, and so on and so forth. That's quite tedious to do by hand. It would be obviously really nice if we could just have ChatGPT do this for us. And so when all this, fascination about ChatGPT started, we then basically asked it, well, do you know the Java modeling language? And it at least claimed that it did. And so we thought, okay, let's test this. And so, as I said, we use the program verifier key for that. It supports a large share of the Java programming language. It's also been used for some case studies. So if we were able to actually automate program verification with large language models here, this could also mean that in the future, maybe if we want to do a case study, we can automate a lot of the work that has previously always been done manually. Now, again, for the people that come from a more mathematical background, just to give you an idea how this relates to theorem proving, essentially you can think of this verification methodology as a theorem proving approach for a particular dynamic logic. A dynamic logic is a modal logic. So essentially, we have a program like max of first two, which in this case basically just computes the maximum of the first two elements of the array. And now if we want to verify that this program satisfies some property, it essentially amounts to proving the validity of formulas in this Java dynamic logic. So essentially, we can write Java programs into a modality and then have some post condition. And essentially what this tells us is that after every program run, where inside this modality, inside this box, is some Java program, some post condition holds. So for example, in this case, we're trying to prove that the result is equal to the first element of the array. Now looking at the program, that's obviously not always the case because the second element might be larger, but then we can basically just add preconditions. And so we have a logic for this. And now the question is, how do we perform these proofs? And essentially there's two ways to this. The first would be to manually apply these proof steps. And the second approach would basically be what is sometimes also called auto-active verification, where we annotate the source code and these annotations then basically guide the proof. So for example, we can annotate the source code with a loop invariant, and then basically the prover will apply a loop invariant proof rule that decomposes into different proof obligations that need to be performed in order to prove the validity of the overall formula. Right, so Java modeling language, I've already talked a little bit about this. You've also just seen Berezun and Daphne. These are other examples of tools and languages where you can do verification. It supports a lot of things. It supports pre and post conditions, invariants, asserts, and so on and so forth. But essentially, our idea now is let's combine large language models, which are sometimes not that rigorous and might produce these spurious outcomes, and deductive verifiers, which have these strong symbolic techniques, but are not good at guessing things like loop invariants and so on and so forth. Okay, so to give you a concrete example what this looks like, I mean, this pipeline will now probably seem familiar to you from the last talk. Essentially, we start off with a Java program which is partially annotated. So for example, in this case, we have the method f. We have a contract for this method f. We will call this the top level contract. In this case, it just says that the result is supposed to be -2 times x. And now to verify this program, we would need a lemma on the behavior of g. And so basically what we would do now is we would ask the large language model to give us a contract for this method g. Then we would get a draft from the LLM, and then we will ask the verifier whether it's now able to verify the correctness of method g and method f. Now in this case, the LLM, or supposedly the LLM, returned if x equals 2, then the result should be 4. That's correct for g. But it's insufficient to prove f, right? Because f is not only executed in the case where x is 2, but also in other cases. So in this case, we then basically give feedback to the LLM and tell it, look, in this case, this is not the result we wanted. And then the LLM will try to refine the specification and maybe come up with something else. And then in the end, we hopefully have an fully annotated source code where we can actually verify the correctness of f. So after we've kind of implemented a prototypical implementation of this with this verification tool, we started an evaluation on this. And now that obviously, similarly as in the previous case, we have the issue that there really is not that many benchmarks out there that we can use for this, because we basically need programs where we already have a top-level specification. Now, obviously, we can't easily just scale it to all of OpenJDK, right? So we kind of need some well-scoped examples to start off with. And what we ended up with is actually the old exercise sheets. So at the university in Karlsruhe for the past 20 years, there has been exercises on specifying Java with JML. And so essentially, we were able to repurpose these exercises as a first test to see how GPT or LLMs in general perform on this task. We kind of split this up into two kinds of tasks. The first one doesn't really come with soundness guarantees. Basically, we just give it the Java code and ask it, okay, can you give us a specification for this code? We can then obviously check whether the specification matches, is consistent with the Java code, but we can't really be sure that the specification is what we actually wanted it to specify, right? The second approach is then the one I think is also more interesting, which is basically we have a top-level specification, we have the Java code, and then we ask it to fill in gaps in the specification. These gaps could either be that loop invariants are missing, or these gaps could also be that we're missing a method contract. Right, so we gathered these benchmarks. Those are kind of some numbers on these benchmarks. So we try to cover a wide range of kind of features. We have quantifiers. We have assignable clauses, which kind of constrain what kind of heap writing you're allowed to do. We have references to the pre-state. So sometimes in an ensures clause, we will say, well, this is the array. At this position, we have the value that was in the array at the beginning of the execution at some other position. We have pure method calls. So in GenL, you're allowed to call other methods, provided they don't have side effects. And in terms of Java features, we also have some cases with arrays and also some cases with field accesses. So we try to cover like a few different things here. Right, so we basically then ran this evaluation. both for GPT 3.5 and GPT 4.0, and already, in my opinion, got insofar some interesting numbers, as this really was not with a lot of prompt engineering. Because, I mean, we only had, for the submethod case, for example, we only had 14 cases. So starting to do prompt engineering there with 3 cases, and you only have 11 left to evaluate, is kind of gets difficult. So we basically just came up with some baseline prompt and did this evaluation. And I think it's interesting to see that already here we're seeing quite an improvement also with respect to GPT 4.0, where, for example, suddenly for 67% of cases, we actually get the right loop invariant. Right, so for the isolated methods case, as I said, for the submethod and the invariant case, we have a very clear quality criterion, right? If this is successful, then we know that the whole proof went through. We had a top-level specification that is now proven. For the isolated method case, that's less clear, right? Because in this case, it might be that it just generates and ensures true. This would be something that we would be able to verify for the method, right? So we kind of have to rule this out. For that, we kind of just went manually through what GPT generated and basically looked at what it produced. And it turns out that actually it always does quite a good job at summarizing what the behavior of the method actually is. In some cases, it will miss something, so maybe it will specify that the method that the elements in the array are now sorted, but not that it's the same elements as before, or something like this. But overall, we were quite happy with the kinds of isolated method specifications we got. We also looked at the kind of errors we observed. And here I think it's also quite interesting to see that, for example, the syntactical errors went down quite a lot from GPT 3.5 to GPT 4.0. So although JML really is quite an obscure language and we didn't do any kind of few-shot prompting, but just like gave it the one-shot case, we see that somehow GPT 4.0 learned this apparently. Conversely, obviously, then if the syntactical errors become less, we have more semantical errors, and then obviously the question is, how do we take care of these? I thought it might actually be interesting to also have a quick demo of what this looks like in practice. So I will try this now, but I have a backup in case this doesn't work. Okay, so I have like a small demo presentation. This is obviously like not the kind of tool that you would want to use in practice, but I think it gives a good intuition for the kind of things we can do. So let's say we have a method here, array set. This has different methods. In particular, it has the contains method, and in the contains method, you're basically given a value b, and you're supposed to return whether this value is part of the array values. Now, in this case, we are missing the loop invariant here, so we can now basically ask GPT, and then basically what we do is we have a prompt here where, first of all, we're kind of telling it, okay, look, this is your task. You're supposed to do JML annotations. Also, first think about it in natural language, and then do the actual reasoning, and then we give it the concrete instance. And actually, now it went too quick, but essentially what happened now is GPT then answered by, first of all, giving some natural language reasoning on what this what the loop invariant is supposed to do, and in particular, it then basically generates an invariant where it's saying, okay, if I'm still in the eth loop iteration, then I can assume that the past iterations have not been the value that I've been looking for. And so in this case, it turns out that this is exactly the invariant you need, and so then Key is able to successfully verify that. The question is now, maybe does this work for everything? One of the cases where we do have trouble getting it to work is a computation of greatest common divisor. So in this case, there's a loop invariant missing here for a helper method. And so far, I don't think we've ever managed to do it. So I would be surprised if it works now. But essentially what happens now is, I mean, it's again making an attempt. And then Key is going to try and verify that. It will probably fail in about 5 seconds. And then we can basically see what happens now, which is that we're now basically giving GPT information on what went wrong. In particular, in this case, we're trying to give some basic elementary information on the proof state, namely which proof branches were left open. We have the methodology of getting like the labels for these proof branches. Okay, so back to the presentation and the feedback. So the question then, obviously for us was, does this feedback actually help? Does it benefit the specification generation if we're giving this kind of feedback? And before we came to this feedback, another thing we actually tried was giving concrete counterexamples. So besides Key, there's also another tool which uses bounded model checking. It's called JGBMC, and it allows verification also of JML. And this tool we basically used to generate concrete counterexamples and then gave those to GPT. Unfortunately, at least at the time we tried this didn't really lead to any satisfactory results, because essentially we would give it a counterexample like this, and then there would happen some natural language reasoning, which would also say something like, oh yeah, this is an array of odd length, so this is actually why there's a problem, and it would be correct that this is the problem. The loop invariant didn't work for odd numbers, but then it still would give a loop invariant that doesn't work. So this is just one example, but there we tried around with it a little bit and didn't really get to anything that was working. And so then our second thought was, okay, can we somehow make use of the proof state? So I mean, for syntactical errors, we can obviously return parser error messages. For the other case, we were trying to give information in open proof branches. And so for these experiments, we now focused on the auxiliary specifications. And essentially here, we then thought, okay, let's compare this to basically just asking multiple times, right? I mean, this is, if instead of giving feedback, we could also just sample different solutions and check whether any of them verify. So this would be like the pass at n notion, essentially, in machine learning terms. And yeah, we ran some experiments on this over 10 iterations. And looking at the experiments, unfortunately, not great news for the feedback we are giving. As of now, it really doesn't help any more than the sampling. So essentially, actually, there's even cases where the sampling is better. My current assumption is that this is because sometimes with giving feedback, the GPT kind of gets stuck at one solution and tries to refine that, although it should actually pivot to something significantly different. Right. But then thinking about this more, we also realized that just looking at these numbers of iterations might even be too friendly to the feedback-based approach. Just to give you an intuition for that, yeah, sorry, I also wanted to say that, yeah, we need more benchmarks because, as you can see, I mean, these numbers are still pretty close, so it would be good to get more conclusive results on that, and for that, we would need more benchmarks. But now about this iteration-based evaluation, if we were thinking about a classical verification technique, and one of the techniques, we would have two variants, and one technique takes 5 iterations, where each iteration takes 2 seconds of CPU time. And we have another technique which takes 3 iterations, and each iteration takes 4 seconds of CPU time. Then we would probably say, well, the one takes 10 seconds, the other takes 12 seconds. So even though we only need 3 iterations, whatever the iterations are, if we wanted to use it in practice, then probably A would be better. The issue with this is that we were using GPT. This usage of APIs kind of hides the computational cost from us, right? So it's kind of, how do we evaluate this? And I mean, one thing we do know is that the computational cost increases with the number of tokens. And doing some back-of-envelope computations, essentially, you can figure out that with the sampling-based approach, we're basically sending one message to GPT n times. And so we kind of have a linear growth in tokens. With the feedback-based approach, we're kind of iteratively increasing the conversation. And so in a way, there we even have a quadratic amount of token usage. So it could be argued that in terms of computational efficiency, maybe the feedback-based approach is even worse if it doesn't then also yield better results. We also did an evaluation on this, where basically we tried to evaluate with respect to normalized token counts. In the top row, you see basically the iteration-based evaluation. And in the bottom row, we're basically normalizing the amount of tokens we used for these two strategies. And what you can see here is that A, we need more data because these lines are too close together, but B, in some cases, the median actually leaves the the shaded area of the feedback-based approach. So in this case, it seems at least a little likely that the sampling-based approach might be performing better here in terms of token efficiency. Right. So as you already saw before, before my presentation, we're not the only ones working on verification of large language-based on verification using large language models. And so I also want to point to some other work in that direction. It's a rapidly growing field of research, so I can't possibly cover everything. There has been a lot of work on Daphne recently, because recently there has been this release of Daphne Bench, which is, I think, probably so far the biggest benchmark set for verification in this large language model domain. Then there's also work on verifying C using ACSL. There's this tool called AutoSpec, which was released last year. They are going beyond filling just one gap by essentially coming up with a strategy to fill in all the holes at once, which I think is quite interesting and definitely something that we are also hoping to go into that direction. They, as far as I can tell, so far they don't use any kind of proof state feedback, judging from our results as of now, rightly so, but maybe we will still figure out how to change that. And they're also using the ChatGPT API, so obviously there similar questions about token efficiency eventually could arise. Another interesting direction that also has been hinted at in the previous talks is co-generation of code and specification by basically generating both at the same time. And there are some results that it seems indicate that kind of generating both of these things at the same time could also lead to better quality, even when you're only having a natural language description in the first place, what you want. Lastly, recently there has also been a release of a GitHub scraped HTML dataset, so this is also something that we definitely want to look into next. Right, so to conclude, what was really surprising to me in this work is that OpenAI's model seemed really good in generating JML, even though we didn't use any kind of future prompting. And to me, that kind of seems to indicate that these foundation models really can also be used for niche languages where there's not a lot of data on GitHub, right? I looked it up at some point, I forgot the numbers, but in comparison to any other programming language, there really is not a lot of JML on GitHub. Nonetheless, even though it can kind of lessen this lack of data issue, you still obviously need benchmark data to then do these experiments. Some open questions that I personally have is, first of all, well, how can we give more effective feedback on the current proof state? Because I think that if that would somehow work, I think that could really make the approach more reliable. And the other question that's still in my mind is, when we're doing prompt engineering, I feel in a lot of cases, people are doing prompt engineering under the assumption that there's no such thing like as a perfect checker, right? So if we're doing prompt engineering for code generation, we're basically thinking about how can we prompt the model in a way that it's going to give us the right code as likely as possible. And then we will come up with agent approaches and with, I don't know, all kinds of fancy things which use up loads and loads of tokens to give the right answer. But with verification, we have this thing where we really have a good way of checking whether a solution is correct. And so for me, there's kind of a question whether then these tokens are better used to just generate more solutions and check all of them. And finally, another question that's in my mind where I don't have a good answer yet is, what are fair comparisons between large language model-based approaches and classical approaches? Because naturally, every time I'm sending these API requests, there's a farm of GPUs working for my verifier, which comparative approaches which do symbolic invariant synthesis or something obviously don't have. Okay, so now I'm open for any questions, and thank you for your attention.
Okay, any questions?
Yeah, so when you were calculating feedback cost back then, where you got the square estimate for feedback, part of it is that your prefix is always the same with feedback, right?
Sorry?
So when you use feedback, your conversation grows, but its prefix is always the same.
So in our case, we kind of grew the conversation naturally. We didn't just use the same prefix every.
Yeah.
But yeah, so like the prefix is the
Yeah.
same as the last round.
And for transformers, this in fact doesn't increase the cost if you use the right APIs.
I guess it kind of, yeah, I mean, it kind of depends on how exactly you're using it then. I was kind of making the back of develop calculation when I'm sending this request to OpenAI, then I kind of use up those tokens.
Yeah.
Yeah, it's a matter like obviously if I were to run it on like in a particular setup where I keep the conversation context, then you're right that
and LLMs usually have conversation APIs that allow you to keep the context without additional cost.
Yeah.
So it's still linear in both cases, if that's acknowledged.
I wanted to ask you two things. So first, you're using Key, so I believe there's also some static analysis in Key. Have you considered using information from the static analysis tools in Key to include in your prompt? And question two, have you considered comparing the results from GPT to DeepSeek?
I would definitely be interested in comparing to DeepSeek. We haven't done yet, but that would definitely be something that we want to do next. The issue was kind of once we had these results, somehow the particular library we were using had its end of life and some technical issues. But yeah, so like integrating some static analysis information could definitely be interesting. We haven't looked into it yet.
I just wanted to clarify how exactly you are sampling ChatGPT without giving it feedback, because this functionality is suppressed by OpenAI. It's quite challenging to do it. So which GPT you are sampling and how without giving it feedback? Did you use temperature?
Well, when I say sampling, essentially what I mean is I ask the same request multiple times.
But then you get the same answer.
0 temperature, and then I get different outputs.
Oh, you put temperature in.
Yeah.
And does it work with GPT-4? I don't think you can put temperature
I've
in.
done it. I mean, I've only done the experiments with 4.0, so I can't tell you that.
With what?
I've only done the experiments with 4.0, so I can't tell you about 4 right now.
Okay, well, maybe we can chat about it.
You can put temperature in one reason models, but not in using models. So all one.
Any other questions? I have other questions if no one else has questions, but I don't. No one seemed to appreciate that.
How similar are the invariants that so it looked like you're generating a lot of invariants and sort of are there other auxiliary lemmas in there or just invariants?
Invariants or like contracts for submethods. There were these two categories, right? Either we generated contracts for submethods that are being called by the top level method, or invariants.
How structurally similar are they across benchmarks? Like, could I build an enumerative search that would find them, for instance?
Right. So, do you mean across the benchmarks we evaluated on, or how structurally similar are they to the top level specification?
Across the benchmarks you evaluated, if you get like an invariant that says that X always like decreases or something like multiple times, like is that in many of the benchmarks or are they all very syntactically unique?
I'm not 100% sure. I mean, like for these array things, we definitely had a few things like sort, find the element, copy. It's not that they're exactly the same, but there's certainly some structural similarities.
I guess my follow-on is, have you thought about RAG or tried RAG?
Not yet.
Yeah. One more question. I'm not going to throw it all the way over there. That's good. Hide your laptop.
Thank you. Okay, thank you for the very nice presentation. So my question is, for more complex scenarios, have you considered, like if you have a complex expression, for instance, in a loop, have you considered following a divide and conquer approach, break it into smaller chunks, then try to formulate the specification on these parts and then eventually connect them together? Because in the cases that are very complex, essentially the model will start not hallucinating, but it will start losing context along the line. So if you break it into smaller chunks, this might be more effective. Have you considered that as an approach?
We've already thought about it. So right now we have a lot of ideas, but like a lot of things haven't been done yet. I mean, one thing you could also do is kind of just to gather all the different atoms that it generates and try to symbolically combine them in different ways to kind of that way search for a suitable invariant. That's definitely something. We also see in the sampling that sometimes maybe in the one iteration it produces the first half correctly, and then the next iteration it produces the second half correctly, right? So if you were able to combine them in a clever way, that would also help, yeah.
Perfect, thank you.
Okay, are there any other questions? If there are no other questions, then we should thank Samuel.
Hi, I'm delighted to host the session before dinner. I'm Yixuan Li, a PhD student from University of Edinburgh. And now we have a session about ethical and philosophical issues in using generative AI in theorem proving. Let's begin with our speaker, Markus Panzer from RWTH Aachen University, who will be presenting on the need for ethical guidelines in mathematical research in the time of generative AI. Markus, the floor is yours.
Thank you very much. Yeah, it's great to end such an inspirational day with some philosophical aspects. I have to say that my approach to philosophy is mostly epistemology. So today I'm talking about ethics, but it's not really my field. The reason I'm not talking about epistemology is that when it comes to automated theorem proving with LLMs, as we've heard today, let's see. We don't know what's going to happen, really. But the reason I do want to talk about ethics is that when it happens, we need to be ready. So that's going to be my underlying message here. I don't need to tell you too much about what this is about because it's been covered already, but we know that there's different AI systems now. OpenAI's O1 was mentioned. Harmonics Aristotle hasn't been mentioned, but it's very similar to what DeepMind's AlphaProof has been doing, and Alpha Geometry 2. And all of them are doing well with the benchmark of the International Mathematical Olympiad, right? I'll be focusing here on Harmonics and DeepMind's applications for one reason, because they're hybrid systems, what we call neurosymbolic AI. So they associate the neural part, the LLM, and the symbolic part, which would be, in both cases, the theorem prover lean, which is a rule-based system, good old-fashioned AI, right? And because they do have, as has been mentioned already, the rule-based system there, we do get robust checking of the proofs. So it raises hope that we might have generative AI systems or these hybrid systems that could be robust in solving mathematical problems. They sort of are already when it comes to these competitions. But the competitions, let's face it, there are always going to be problems that already have been solved. So how valuable is that in terms of progress in mathematics? It's a very interesting development, right? But no mathematician is going to be stunned by this in terms of progress in mathematics. It's progress in computer science, progress in AI, but not really progress in mathematics, right? But this might, of course, change. So I'm going here into this dimension that one of the keynotes talk about as a future, what might be happening. So what if we could have a genuinely new mathematics generated by one of these AI systems? We could use it to provide new proofs for theorems. I mean, we can already do that, but what if this could be genuinely interesting new proofs? Or even in the best case, we could prove original theorems. And ultimately, as the sort of aim of this sort of development, could we have what I call autonomous automated theorem prover? So something, an AI system that's trained on mathematical texts, provides humanly interesting proofs of humanly interesting theorems as the output. So basically the scenario where we train it, we no longer do anything after that, and we get interesting mathematics out of that. You all know the technical parts. Usually when I talk to philosophers, I need to explain this, but the problems have already been mentioned. So at DeepMind, for example, what they did, of course, was use the million informal problems to create this huge training data set of 100 million formal problems. This was the deep proof, the alpha proof method. But we can't really do that with our known methods, at least when it comes to humanly interesting mathematical proofs. We are probably around thousands of proofs, or maybe at most tens of thousands of proofs that we consider to be humanly interesting. So we would need to multiply this by several orders of magnitude. How can we do that? How can we still generate something that is humanly interesting mathematics? So that's one problem. Another problem is that the way LLMs are structured is, of course, to be very predictable. That's what we want from them, that they don't give outliers. They give something that we can recognize as desired outputs. And that sort of goes against what we want from new mathematics. In mathematics, we want creativity. We're going to hear more about that in the next talk. But we want something generally interesting, new content. But LLMs are, of course, not designed to do that. Well, these are problems. I'm not going to downplay the importance of those problems, but at the same time, even those problems notwithstanding, there don't seem to be any reasons why progress couldn't be made in AI theorem proving. Of course, we've already made a lot of progress, but further progress into this sort of autonomous direction. And the new theorems or the new proofs they may be incremental progress rather than some kind of revolutionary new field of mathematics emerging. That I see as a very unlikely scenario. But incremental progress is still progress. And it might be substantial enough to warrant publication in mathematical journals. And this is the scenario that I want to focus on now. Because if this happens, then a skilled user of these AI applications can now have access to something that never existed in the history of mathematics before, a machine that can generate mathematical proofs and theorems. Well, you probably already see where I'm going, because this was supposed to be about ethics. Well, in such a scenario, this person, the skilled AI user, could now get credit for a proof while it was actually AI that was doing all the important work. If we are not prepared for this, if we don't have discussions about what that means and what it means to be a mathematician, this can create severe injustice in terms of publication records, first of all, and ultimately, due to that, mathematical careers. We can have professors who were just the first generation to be able to use these AI tools in a fruitful manner. Indeed, I'm not so sure that this is not happening already. Whether it's happening already or whether this is in the future, whether it's 5 or 10 years, I think this is the time to establish ethical guidelines, how we should use these AI applications in research mathematics. And these guidelines just don't exist. There's guidelines about using large language models for generating text, but not for mathematical content. So in a recent paper, I proposed that let's start formulating mathematics-specific guidelines for the use of generative AI in this sense. And rather than coming up with something completely original, I decided to follow established practice and what is now being suggested for general scientific guidelines. So I follow the work of Resnick and Hosseini in also a very recent paper. So now I'll just propose their guidelines and my mathematical version of them. First, their first guideline was that researchers are responsible for identifying, describing, reducing, and controlling AI-related biases and random errors. Of course, this is also applicable if you use large language models in mathematical AI. But also, it might not be as big a problem as in many other fields. For example, gender and racial bias is probably not going to be a similarly important problem. Although, of course, there's the geographical angle. Usually we train this system from geographically speaking rather limited material. And that's how it's in the case of mathematics most likely as well, even though we don't really know how these systems have been trained. So we need to be sensitive to inclusivity and diversity also in this case. Second guideline, researchers should disclose, describe, and explain their use of AI in research, including its limitations, in language that can be understood by non-experts. And of course, this is applicable to mathematical AI. Sorry about mentioning the 4 scenarios. I needed to cut those for time. Anyway, we should have done this already, right? We use interactive theorem provers or automated theorem provers, proof assistants, and that's used without making any note in the paper. So why didn't we already have this, that we should disclose what kind of AI tools have been used in the mathematical reasoning? But definitely when the use is becoming more and more substantial in the sense of generating the mathematical content, this should now be imposed quickly. Third, researchers should engage with impacted communities, populations, and other stakeholders concerning the use of AI in research to update their advice and assistance and address their interests and concerns, such as issues related to bias. Okay, now it's very difficult to determine what the scope is. Mathematics is sort of used everywhere, but modern top-level research mathematics, a lot of the time, not really. So how are we going to determine the scope? But at the very least, we should now focus on the relevant institutions of research mathematicians and universities. Fourth, researchers who use synthetic data should A, indicate which parts of the data are synthetic, B, clearly label the synthetic data, C, describe how the data were generated, and D, explain how and why the data were used. Now just replace synthetic data with AI-generated proofs, and there's a guideline for mathematical research. Last two, AI systems should not be named as authors, inventors, or copyright holders, but their contributions to research should be disclosed and described. This, of course, has to do with responsibility, who is accountable if this is somehow wrong. So we can't hold AIs accountable. They shouldn't be authors, right? This is the only one that's currently often said in mathematical guidelines, but it's not very clearly stated. It's just said that this should be disclosed. What I propose is something very, very open. It should already be in paper titles. If your paper has used AI tools, it should be there in the title, and it should be specified how it's been used. So my suggestions here are something, an AI-assisted proof, or an AI-generated proof, or in the most pragmatic sense, an AI-generated theorem and proof. Theorem here meaning conjecture. And finally, the sixth one, education and mentoring in responsible conduct of research should include discussion of ethical use of AI. Well, I don't need to tell you that this should be directly applicable to mathematical research and definitely should be part of the curriculum, even though it isn't. Thank you. That's the paper where you can find the details of all this.
Thank you, Markus. There.
I'm a little bit confused about why you feel that, so in a mathematics research paper, let's say a published mathematics research paper, presumably other mathematicians in that area can check the proof and make sure it is correct. And you're saying that it should be the responsibility of the authors there to reveal all tools, as it were, that they used, right? But we don't really do this with calculators, and we didn't ask, I don't know, people 100 years ago to tell us whether they used an abacus or not. This is just a tool, and at the end of the day, the product that's being produced is a hopefully self-contained mathematics paper with proofs that can be checked by others. So why does it really matter, as long as the proofs hold up, why does it matter that we used one tool or another in order to arrive at that?
Okay, thanks. So that's why I said that I'll be talking about the ethical dimension, not the epistemological dimension. So from the epistemological point of view, it probably doesn't matter we just want to get good mathematics out of it. And that's fine. But at current time, we expect some kind of mathematical expertise from mathematicians. And that expertise is not just using an AI tool to generate proofs and theorems. So that's why I'm talking about this ethical aspect of authorship, because now you could, as I mentioned, you could sort of create a career seemingly being a good mathematician, but actually you're just a good user of AI tools. Now that might be the future of what mathematics. Yeah, that might be the future of what being a mathematician is, but it's not the present. And before we know how to deal with these issues, we need to be open about the use. That's my point.
Okay, but my point is that ultimately the task of a mathematician is to produce those theorems, however way they do it, to produce interesting theorems, as it were, that others will consume and so forth. However way they do it, that is their job. They've done their job, even if they've used those tools. So you seem to suggest that, oh, they're cheating if they've used those tools. But we don't think of using a calculator as cheating when we're
yeah, exactly.
Well, if the students use ChatGPT to generate text where I'm evaluating it in a subjective way, that's completely different than somebody producing a mathematical proof that I can check to see that an interesting theorem that I wanted to prove is being proved. Who cares if it's, I mean, what do you mean original? I mean, the originality, what I mean by originality is we have the same mechanism for scrutinizing these. They submit it to a journal, we evaluate it at the journal, and if it is accepted because it's deemed to be original by other humans, right? I don't understand why the involvement of a tool, just like a calculator or an abacus or whatever, should make that less worthy of, you know.
I'm not saying it's less worthy. It just should be disclosed, because calculators, okay, we accept them, but we don't know yet how we evaluate the use of these tools, because the tools aren't really there yet. So I think that's what I want to say. But because you also have standards like plagiarism, you wouldn't accept that, right? And some people would consider this closer to plagiarism than using a calculator. So I'm just saying that we should talk about this. We should have the discussions now before those tools are regularly in use.
If I may move that a little bit further, can you go back to your last slide? You say AI systems should not be named as authors, inventors, or copyright holders. I mean, I agree with the current bunch of ChatGPT and so on, but assume we get a real AGI in the future, an actual human level AI system. Why shouldn't that be named as an author or inventor? And maybe that also goes in your direction. If the system is so smart that the human is merely pushing the button, create a theorem, create a theorem, create a theorem, should he get credit for that?
Well, if at some point it's so smart that they don't need us in the loop in the first place, then no. But to the extent that they need us in the loop, and somebody's making some effort and getting something out of those tools, these are just tools that humans use. I don't see the difference between a calculator and I just don't see what is the difference. They're just tools for our purposes.
Yeah, okay. But to answer a question, in that case, I suppose we should reconsider authorship. But that's one big thing in AI ethics is AI control, of course. And that's almost like axiomatic now among AI ethicists, that we should never lose control of these AI systems. So this promoting AI agents to sort of on a level par with human agents is something that is very heavily opposed by these people. Yeah.
Most scientists like Star Trek. There's a great episode of Star Trek Next Generation, maybe the first good one, called The Measure of a Man, where they discuss if the Android data has the right to determine its own future. And it's a very compelling story, and it's deeper than it looks on the surface. But isn't that something when we say we shouldn't lose control? But if you're building more and more intelligent AIs, where's our moral justification for controlling them coming from?
Yeah, okay. But then there's a bigger question, which is that how do we impose responsibility on this AI agent? So if we are ready to give them agency in this sense, then we also need to somehow demand responsibility from them, and that's a huge discussion in AI. Yeah.
One more question.
The next speakers come down at the same time.
Could you say something about provenance? You didn't say anything about provenance. So, for example, the AI might give a great result because it was trained on some particular research papers, but surely those papers should get credit, no?
That's a good. Well, yeah, the training data problem is interesting here. Anyway, so I think they should get credit in the sense that they've been used for training it, just like any author whose work has been used to create these large language models should somehow be credited for that.
But now there's an onus on the developers of the LLMs to track provenance, to be able to say to you, hey, this result we're giving you depends mostly on these particular results that we use for the training.
That's going to be very, very difficult to identify, of course.
But otherwise we're completely upending the whole tradition of giving credit. When we write a paper, we have references and we cite those people who've inspired the work we've done. And if that connection is broken, that seems like it's a huge step in a maybe very undesirable direction.
Yeah, I agree. That's a really interesting point, because the way we have always done science, including mathematics, is to build on tradition by referencing earlier work, and the whole AI assisted science thing is going into a different direction, because providing proper references is very difficult for these systems, even with these systems whose main purpose is to do exactly that. So I think we're on sort of a dangerous ground of losing out on these ideals that we have in research, also in mathematics. That's a good point.
Thank you, Marcus. Let's have the discussion.
Thank you for having me here. Hello, everybody. In our institute, we have a group working on responsible AI, and because of my mathematical background, I work on creative AI in mathematics. So AI is increasingly integral to mathematical problem solving today, and there are various opinions on this. For example, some of them are extreme. One of them is AI may substitute mathematicians at some point, or the opposite one is just another tech bubble. I believe that the plausible point of view could be that it's a powerful tool, but not a substitute for human creativity.
So there is a microphone.
This one? Yeah? Oh, thank you. So today I have two aims of my talk. First, to give you some conceptual framework and invite you for discussion about creative AI. So the questions I'm going to address today are: can AI solve problems creatively like a human? And what defines creativity? And the new question I think I raised today is: how actually can AI affect human creativity? So overall, there are three areas of AI impact in mathematics today. It's optimization, proof assistance, and machine learning, such as identifying patterns. And interestingly, AI can provide a bigger picture and help to structure mathematics. And also it can help formulate new research questions and conjectures. But so far it's still augmenting human work without replacing creativity. AI has its strengths, of course: speed, efficiency, consistency, and accuracy, data processing. It can handle huge amount of data very quickly, and it shows good results in terms of identifying similar problems and solving clusters of problems. But it has its weaknesses, of course, which is lack of intuitive problem solving. It cannot understand, as we saw in the movie. It relies on algorithms and prompts and struggles with abstract concepts that require intuition and broad experience. It has difficulty in handling ambiguity, which often helps human creativity. How can we define creativity? Actually, there are many definitions, and all of them are context dependent. In general, a creative solution must be innovative to the current system or practice. Well, the traditional common view is that human creative solution crystallizes in the unconscious. However, the father of AI, John McCarthy, suggested a demystifying definition, namely, a solution to a problem is creative if it involves concepts not present in the statement of the problem. So his definition is agent neutral, and it relates to so-called conceptual blending, which is combining or adding a new and unexpected feature to an existing concept. To demonstrate to you, I present a famous example, mutilated chessboard problem. The problem states, is it possible to cover the grid, 8 by 8 grid, with two opposite corners removed by 2 by 1 rectangle? So the exhaustive search would take you a couple of lives, and presumably, well, definitely it's a computer assistant proof. But humans came up with a solution which I called a thought experiment. So it says, imagine a grid, the grid to be an 8 by 8 chessboard with deleted diagonal corners. So the new formulation of the problem would read, is it possible to tile the 8 by 8 chessboard with two opposite corners removed by 31 dominoes? Well, I can't give you time for solving this problem, but the answer is no, because the two removed corners are white, both, and a domino always covers two colors, black and white. So it means that there will be some two black corners, two black squares, which are not covered. Yeah, you can think about it later, but why is it important, this kind of solution? Well, because it's elegant and rigorous, and we want our mathematics to be elegant and rigorous. And also, all the automated proofs with reduced complexity appeal to the hint of coloring. And moreover, some relevant related problems were also solved by using this coloring prompt. So is AI capable of such conceptual blending? There is some work done on this problem. I have this reference which include a review on such research. But I am skeptical about this, first of all, because creativity, artificial creativity comes at the cost of reliability. So LLM is not, AI is not a reliable assistant in such problems. I tried myself 3 of them, including ChatGPT, and they're simply lying. And the second more important argument is that, well, even if we succeed in conceptual blending, even if AI, if we can delegate some of it to AI, anyway, creative solution has 2 phases, which is first generation phase when all possible blendings can be generated by AI. But the second one is evaluation phase, when the generated constructs have to be evaluated for meaningfulness and usefulness. And this, I think, is primarily human function. On the other hand, in doing these evaluations, humans can be restricted by some subjective considerations, whereas AI has no psychological limits. Just to give you a historical example, Gauss, being concerned with his academic reputation, didn't publish his findings about non-Euclidean geometries. And Lobachevsky, when he published his work, had such problems. So the conclusions I'm drawing today are that AI could potentially be a creative tool, but inherently thanks to human prompts. And we have to think about balancing strengths, use AI for managing data and calculation while preserving human intuition and abstract reasoning. And I think most importantly, we have to think about co-creativity with AI. The future lies in collaboration between AI and human mathematicians, such as AI aids conceptual blending, humans select, but we may improve our evaluation of creative solutions. Thank you. That's it.
We can only have 2 quick questions, otherwise people are starving.
Thanks. So there are various, of course, mathematical theories of what it means to be creative. I don't know if they're any good, but some come from information theory and some are even used in machine learning and AI. We saw an example of one of them earlier in the context of intrinsic motivation. So it seems in principle possible to me that you would have some kind of AI system, possibly a more sophisticated one than the ones that exist today, that does, exhibit some kinds of creativity, possibly because, it's trained with a loss function that encourages it. And, there are people who've done studying on that kind of thing. Do you see the future going that way, or do you still think there's something ineffable about what humans contribute?
Yeah, thank you for your question. I think, well, as I said, I think we can delegate to some extent, but it's an open question to what extent. And actually, I'm inviting you to share your opinion, how much we can give for conceptual blending. Presumably, AI can combine everything with everything. But, and presumably, we can also teach AI to evaluate according to some criteria, some maybe most fundamental criteria, but nevertheless, we have to control. That's my opinion. Yeah, thank you.
One more question.
Yes. Thanks. Well, we had earlier in the conference about interesting problems, so I think that this talk is really interesting. Well, I'm a little bit biased, but it's interesting because it doesn't involve complicated mathematics. Everything is transparent. It was actually recreational math problem. So it's below Olympiad level. It's not high complexity, so the counting for this problem is not more than exponential, 4 in the power n. So it's not too complex and not complicated mathematics. Yet ChatGPT very miserably fails on this problem. I'll have a poster about this, how it fails. If you're interested, will talk to us. Well, basically, it knows the answer. It knows both a stupid way, exhaustive search, and the smart way, which Irina describes. Yet it does not understand the concept. So if you change the problem just a little bit, it would completely fail. So if you ask it, for example, not opposite corners, but corners on the same side, it will give you linguistically correct English, but complete rubbish mathematically. So just totally fail. It's not just it cannot create. It can create with small mistakes lean programs to test existing solution, but it completely fails to understand this new idea and apply it basically. And if it would be a student doing this, I would say if it doesn't do lean programming correctly, well, it's like a B. But what ChatGPT does on this question, on related questions, is like total fail. So if you are researching on using large language models on arithmetic proofs, maybe you talk to us about this, because I mean we are not expert in arithmetic proofs, but what I saw is that it's like very serious failure on quite simple problem, which doesn't involve complicated mathematics. So I think it's interesting. Thank you.
So the final session is over, and are you ready for dinner? And let's go.